Hey guys, now that we know that sound is a wave, it's a periodic kind of compression or longitudinal wave produced by something that shakes or moves periodically. This video is going to talk about different things we can quantify about sound waves, like the frequency, the period, the speed of the wave, or the speed of sound moving through air, or other things like the wavelength. So we've already talked about a tuning fork. A tuning fork, when you strike it, even though you can't see it, the tips are shaking back and forth like this. And when the tips shake back and forth, they're kind of compressing the air, and that compressed air moves away, or where the air is compressed moves away from the edge of the tuning fork throughout the air. And that's essentially what sound is. So if I hit the tuning fork and bring it close to the microphone, you guys can hear the sound that's created. Well, what's the wavelength of that sound? What's the frequency of that sound? What's the period of oscillation? And how fast is the sound traveling through the air? That's what this video is going to help us figure out. So the sound that's coming off of this tuning fork when the tips are vibrating back and forth and compressing the air, it's kind of hard to figure out what is going on with the air particles just by listening to the sound that's created by this. Once again. So we're going to use a second microphone to record what's happening to the pressure of the air particles in the air. And so a microphone is just something that essentially tells us when the pressure is high, when the pressure is low, or when the pressure is staying about constant. And so I'm going to strike this tuning fork on the rubber. I'm going to let the sound kind of come off of here, and this is going to record how the pressure changes over time. So if we look at the graph in the screen, up in the corner of the screen, you can see the pressure right in front of that microphone is staying at about 2.5 units of pressure. That's just some arbitrary unit of pressure. So let's find out what happens when I strike this and bring this in front of there. How does that change the pressure over time? Let's find out. Okay. So you can see in this, the corner of the screen what gets created. The pressure versus time graph kind of looks sinusoidal. It looks like a periodic wave, but what's being plotted on the y-axis are units of pressure, and on the x-axis are units of time. That whole graph up there is only showing how the pressure changed over time for 0.03 of a second. And so all of that motion where the pressure got higher and lower and higher and lower several different times, went through several different periods of oscillation that happened in just 0.03 of a second. So we're going to take a closer look at this graph to see if we can figure out from that and some other information what's the period of oscillation, what's the frequency of that periodic wave, which will give us the frequency that this periodic wave was disturbing the air as it moved back and forth, how fast the sound was traveling through the air, and what's the wavelength, how far apart are those pressure crests, or the regions where the particles are spaced closely together, moving through the air, how far apart are they spaced? Okay, before we use our pressure versus time graph to figure out things like the period of oscillation, the frequency of oscillation, which would be the frequency of disturbance of the tuning fork, the wavelength, and something like the wave speed, I want to take a minute just to remind us conceptually what's happening with the tuning fork and what is it that the microphone is actually picking up. Like, we're seeing the pressure versus time graph, but like, what actually creates that variation in pressure, high pressure, low pressure, high pressure, low pressure, like this? Well, remember, the tuning fork, when it's producing sound, the tips of these tuning forks are shaking back and forth in a periodic way. So it's going back and forth and back and forth and back and forth. And when it's doing that, it's colliding with the air molecules next to it, and it's kind of scrunching them together, pulling them apart, scrunching them together, and pulling them apart. Those regions where they're like tightly packed are moving off at, well, the speed of sound from the tuning fork in all directions. So the sound is spreading out to the right, the sound is spreading out to the left. Well, the microphone is over here, and the microphone is able to essentially measure the pressure of the air right next to the microphone, or the sensor inside of there, at each instant in time. And then Logger Pro allows us to see how did that pressure at that position right there change as a function of time. And so let's just look at the air particles next to the microphone. What are they doing? Well, you can see like where the arrow is right here, it's packed together, spread apart, packed together, spread apart. As the sound waves are moving by there, there's like a high region of density and a low region of density. Like the spacing of the particles changes, and pressure is related to how much force that the particles exert when they collide with the microphone, like for a given surface area. And so when the particles, when there's like a high density of air next to the microphone, that means it's pushing a lot for a given surface area, which is essentially is a high pressure. And when the particles are spread out more than they usually are, they're exerting less force for that given area and less pressure. And so like low density, spread out particles will exert a low pressure on the microphone, and closely spaced particles, where there's a high density, will exert a high force per unit area or a high pressure on that microphone. And so if we look right here, if we were to graph over time, what's happening to the density and therefore the pressure? Well, it's high, low, high, low, high, low, based on that. And so that's what gives us our varying pressure versus time graph that we collected over here. So let's look at that graph closer now to see if we can quantify things like the period, the frequency, the wavelength, and the wave speed. So here's our pressure versus time graph. And over here, I have above it kind of a reminder of what the spacing of the particles were at each instant as we move from left to right on the graph. So we're first going to identify like where are the pressure peaks and where are the pressure troughs. Well, I've identified the first two. The pressure peaks are where the pressure is higher than normal atmospheric pressure. This horizontal dashed black line represents what the pressure is of the air in the room when we took the measurement in general. If there was no sound playing and we recorded the pressure, we'd essentially get a flat line at about 2.5 units of arbitrary pressure. When the sound is moving past the microphone, though, it's changing the density of the air, the spacing of the air particles, and therefore it's going to change the pressure from high to low to high to low. So here we've identified the first two pressure peaks, the maximum pressure of the particles at the microphone. And here we can see two troughs. Right, there was a trough at about 0.02 of a second and another trough at about 0.06 of a second. So there's about 0.04 of a second difference from when the air is like at its lowest to again at its lowest, or about 0.04 from its highest to another instant of its highest pressure. And what is that? The amount of time for one complete cycle of oscillation. That's our period. So this time right here, the difference between the time of one trough to another trough or the time of one peak to another peak is known as the period. And remember, we use a capital T to represent that. So the period of oscillation is about 0.04 of a second. Well, if we know the period of oscillation or of a periodic wave, and sound is a periodic wave, it's just a periodic longitudinal wave, we can figure out what the frequency is, because the frequency is the inverse of the period, or the period is the inverse of the frequency. So here's our equation. Frequency is equal to the inverse of the period, or 1 divided by capital T. So we take 1 divided by 0.004 seconds, and we get about 250 inverse seconds for the units. And remember, an inverse second is the same thing as a cycle per second, which is what a hertz is defined as. And so the frequency of the periodic wave created by the tuning fork, which is the frequency of the sound wave, is about 250 hertz. And why does the sound wave have that particular frequency? Well, it's because the tuning fork was vibrating or moving back and forth at that same frequency. Because the frequency of a sound wave that gets produced will always be the same frequency as the thing producing the sound. And so the tuning fork was vibrating at about 250 cycles each second, and that's actually pretty close to what it was designed for. It was designed for, and probably is vibrating at really close to 256 hertz, or 256 cycles per second. Because we have a little bit of experimental error, we got pretty close to that, about 250. So that means when the tuning fork gets struck and it's producing a note, or the sound, the ends of these things are shaking back and forth 256 times each and every second, which is pretty incredible. which is why when you're looking at a tuning fork, the edges, when it's producing a sound, you can't see them moving back and forth. It just kind of looks blurry if you look really closely at the edges of a tuning fork that's producing a sound. That's because it's shaking back and forth so fast, our eyes can't track its motion. Okay, so now we've got quantitatively the frequency of our sound wave, or our periodic wave. How big is the wavelength? Well, remember, we have an equation to calculate the wavelength of any periodic wave as long as we know the frequency of that periodic wave and v. Remember, that's the speed of the wave, the speed of the pulses, or the speed of the periodic wave, which is moving through the material or the medium. Well, we calculated the frequency is about 250 hertz, or 250 inverse seconds, but how fast are those pulses, those periodic waves moving through the air? That's something we're going to have to figure out first before we can calculate what the wavelength is, how far apart the crests are from one another, or how far apart the troughs are from one another. So to measure the speed of sound that travels through the air, or any pulse, pressure wave that moves through the air, we're going to use a dog clicker. It creates a very clear, distinct sound and a very clear, distinct pulse. And so we're going to use a microphone to measure the shape, essentially, of the pressure wave that gets created by this clicker. So look at the screen. You can see that's what one single pulse looks like. We're going to set up a situation here where I'm going to do this clicker in front of this tube, and the sound pulse that gets created by this clicker is going to go out in all directions in the air, but it's also going to pass into that tube. And 2 meters down at the end of that tube, there's just a flat surface, and that sound pulse is going to reflect off of that flat surface and come all the way back out here. And so this microphone is going to pick up the sound going into the tube and pick up the sound coming out of the tube. It's essentially the echo, the sound wave bouncing off the back of that tube. And so let's see if we can find out what does the microphone pick up when we get the sound coming in and the sound coming out. We should be able to figure out that time delay between when it goes in and when it comes out, and how far is that sound traveled from the first pulse to the second pulse. Well, it's going to be twice the length of that tube, so it's going to go 2 meters in and 2 meters out. So let's find out what is the time delay between the sound coming in and the sound coming out that the microphone is going to measure. So here we go. There you go. You can see on the screen the microphone picks up the first pulse, and that's kind of what triggers the data collection over about 3/100th of a second. And we can see that there's obviously a little bit more than a 100th of a second between there that it takes the sound to travel 4 meters. So let's go ahead and calculate what the speed of that pulse was moving through the air, which will be the same as the speed of any pulses moving through the air, even including that produced by the tuning fork. So here's a little diagram of what we just saw. We're producing a pulse, an individual pulse, using our little dog clicker, our trainer, and those sound pulses are moving off in all directions. These lines just represent regions of high pressure, and in between be regions of low pressure. So as the sound moves outward, and it's going to move past, let's say, the microphone at position A, and it's going to produce an individual pulse. And some of the sound, when we put the microphone in front of that tube, which was 2 meters long all the way to the end, we get sound that goes past the microphone at that position, hits the back of the end, and reflects off, or there's an echo, so the sound bounces off and comes back. And so it's going to move past the microphone twice when the sound will move past the microphone twice when it's in front of the tube. So here's just a reminder of what the sound, the wave pulse looks like when we're graphing how pressure changes as a function of time using our microphone. So at position A, when there was no reflected pulse, here's that individual pulse. And then when we did it again in front of the tube, it looks something like this. And so here is like the leading edge of the first pulse created by the clicker, and here is the leading edge of that reflected pulse that bounced off the back of our tube. And notice there's about a little bit more than 100th of a second, like we saw, and more specifically, using Logger Pro, we find out that it's about 0.0117 seconds. And so if we want to figure out the velocity of the sound, and sound moves through the air at a constant speed, assuming nothing is changing about that air, like the temperature. And so if we want to calculate how fast it's going, we need to take, well, it's a known displacement divided by time. And that sound, like, we know how much time it takes to go from like when it first passes the microphone to when it next passes the microphone. So how far did the sound get displaced? Well, it travels down the tube once and then back out the tube again. So its displacement is twice the length of the tube. So it travels 4 meters, and we measured that it took about a little over 100th of a second to do that. So if we take 4 meters divided by 0.0117 seconds, we get that the sound, that pulse created by the clicker, must have been moving at about 342 meters per second. Right? That seems really fast, but think about it. That sound traveled 4 meters, and it did it in about 100th of a second. Well, a little bit more than 100th of a second. And so it's traveling really fast, like 4 meters in 100th of a second, approximately. Turns out, here's our experimentally measured value for the speed of sound. Well, what's the accepted speed of sound in air? Well, it turns out it's really close to what we just calculated. So if the air is at 20 degrees Celsius, which is about room temperature, the accepted value for the velocity of sound in air is about 343 meters per second. Converted to miles per hour, that's 767 miles per hour. And I'm sure you've heard of like Mach 1 or Mach 2. Mach 1 is 1 times the speed of sound. Or if something's traveling at Mach 3, that means it's traveling at 3 times this speed, or this speed. So now we can go back, now that we know the speed of the pulses that move through the air, whether that's the speed of the sound created by the dog clicker or a periodically vibrating tuning fork, the speed of the sound, or the wave speed, is about 343 meters per second. We'll just use our accepted value. And so wavelength, the wavelength of any periodic wave, is the speed of the wave divided by its frequency. So we take 343 meters per second divided by 250 hertz, or inverse seconds, and you can see that the inverse seconds cancel and we're left over with just units of meters, which we should since we're solving for a wavelength. Turns out that the wavelength of the sound wave created by our tuning fork was about 1.37 meters, which means if we were to, those sound waves, or those pressure waves, are moving out at 343 meters per second, incredibly fast. But if we could freeze the particles of the air for 1 instant in time, and we were to measure how far apart are the high pressure regions located from one another, let's say from where they're really closely spaced here to here, the distance between those regions would be about 1.4 meters in length.